Okay, folks. Hi, my name is Jack Summers, and I'm going to talk to you about using the graphic user interface for the WheeStat 5.4 potentiostat. So, in order to run the graphic user interface, you need to have the executable file, which needs to be in a folder that contains the data file, the library file, and the source file. The data file contains some of the logo information and buttons and such. So it's not a data file for your voltammetry data, but it's what the experiment requires. All right, so to run the potentiostat, run the GUI, you'll either double-click on the executable file itself, or you can create a shortcut, which I have over here and put on my desktop. Double-clicking on the shortcut opens up the graphic user interface. So this is the graphic user interface. The first thing we have to do is connect to the instrument. We select the appropriate communications port, which is in this case communications port 30. Pressing the connect button connects to the instrument. Now we need to select an experiment, and right now for this demo I'm just going to use a voltage ramp. It goes it ramps the voltage from an initial value in millivolts to a final value in millivolts, and as it's set up now we are running from minus 400 to plus 400. Alright, now we're running. Okay, so you can see that we started at about minus 400, and we're going to run down until we get to about plus 400 millivolts. And that's the behavior that we expect to see, because what we have done is to connect the leads of the potentiostat to a 38 kilo ohm resistor. Alright, so since we're just pushing voltage across the resistor, we expect there to be a linear relationship between the current that we're observing and the voltage that we input. Okay, so as we said, we can change the initial and final voltages. So changing our initial voltage to 200 and going to minus 600 millivolts. We can run the experiment under those conditions, and you'll see that we'll be going not from left to right this time, but now we're going from right to left. And as you can see, we went from about 200 to minus 600 millivolts. Alright, in addition to changing the voltage limits, we can change the current gain, and I'm going to now change the mode from being no overlay to being an overlay mode so that we can compare the two voltammograms. And I'm going to go with a gain, which is the amplification factor. It was at 10, now it's at 2. So to show you what the voltammogram looks like when we are at a gain of 2, you can see that there's a lot of noise introduced into the response when you have a low gain. That does not mean that you can go infinitely high. Values, I should say that the values allowed for the current gain range from 0 to 30. Okay, so if we make this about 25 and run, I believe that's going to be too high a gain, and we're going to see loss of our signal at some point. So you can see that we had started out down here and we recorded until we got to this point, and then it flatlined. And it flatlined because our current that we are trying to observe is outside the limits of our detection. That being the case, we got the error message that you can see up on the top. Okay, so there's a couple of ways we can deal with that. We can turn this down, and alternatively we can give it a negative offset. So giving it the negative 10 offset, we will shift the voltammogram downward. Now this introduces an error, an offset error, so now we're below the value where we should be seeing. Obviously, if we have the same voltage limits, we should have the same Ohm's law behavior for the current being passed across the resistor. This is a technical problem that we are working on. We'll get this fixed. It's just where we are in the development phase. Okay, so that is a number of parameters that we have. Let's go back to no overlay, and so we'll clean this back up. Go to 0 offset. And how about a 15 gain? And now I should say that when we hit the run button, it turns into a stop button while it's running. And I can hit the stop button and it'll stop the acquisition of the voltammogram. Hitting the run button again makes it go back and rerun the spectrum, rerun the experiment. Next thing I want to talk about is saving the data. Alright, so we have now acquired a set of data, and we can save that data as a comma-separated file, comma-separated value file, CSV file. And you can see that clicking on that button opens up a dialog box that allows us to check our path that we want to save to, and allows us to specify the name of the file. Okay, so this is 38 kilo ohm resistor, and we'll say that this is file number 4. If we call it a CSV file, then there will be no question about what it is when we go to open the file up. Alright, unfortunately it's got a button that says open, but actually what it does is it saves. Alright, so let's see if I can find where that file is. There it is. Okay, that's it there. Double clicking on that opens up Microsoft Excel and shows us the data that we just collected. So deleting that information, oops, missed one, delete that one as well. We can now plot this in any way that we want using Excel. Boom. Alright. Okay, so yeah, I guess I should show you that you save this. You want to save it as an Excel file, so if you do that, then it'll save it as it'll save all your information, including your graphs and everything, as an Excel file. Alright, so I think that is everything I wanted to show you about the basic fundamentals of running this experiment. There are a number of different experiments that we will talk about: the cyclic voltammetry, the differential pulse experiment, the chronoamperometry, 1 and 2 steps, and normal pulse experiments. And I'll show you some data logging using anodic stripping or cathodic stripping voltammetry. So I guess that's pretty much what I wanted to do.